Morning all, my name is Antoine and I've been working for Ramco for not too long. Before I started working for Ramco, I had a background as being a vendor. This gives me the opportunity to work with various platforms, hardware, technologies, and different customers. Right. So basically, what I'm covering today is something that started as an experiment and got out of control in a good way. I'm not talking about generic automation. I'm talking about automation to solve issues. People here only talk about acquiring hardware, running the application, and everything is like wonderland. Only rainbows, nothing can go wrong. So maybe you can call this a disaster presentation because I only talk about misery and things that always go wrong. Right, so in a nutshell, this is the outline. I will touch two automated systems that are in-house developed. One of this is to collect or gather failing hardware components in systems, and the other one is to analyze the results of the job and then do correlation and do something very interesting that will help us in the future reduce problems even more. In a nutshell, the outline. Right, so what is automation? If you Google it, the first hit you end up in Wikipedia, and it says that anything that is reduced human intervention. I say that because I'm pretty lazy in nature, is that if you do something twice, you can automate it. It's either automation by scripts or machinery, but you can automate it. Because in the end, everybody wants to sit back and drink coffee, right? Right, okay, so in HPC there are like common activities, and I just put a quick outline as in what kind of activities are common to HPC communities, environments, and what can be automated. So the lower you go in this, how you call it, ratio or margin, the lower you go in this region, the more likely you can automate it. Especially here, this is something you can really automate since clusters contain the same kind of compute nodes, and if you're lucky, you run the same kind of jobs. In our case here, I'm using that as my benefit. Right. There are mainly two cycles. This is Wonderland cycle. Here you have your data, you're doing some computation, and you go back again. This basically defines HPC in a nutshell. You have data, you do computation, you go back. You do computation, you get data, you go back. This is the disaster or misery timeline of flow. This basically makes money. I mean, you're doing computation to in the end get the results to do something with it. This is a lost cycle. I know it only costs money. You still you have to still supply power to these machines. You still have to invest time. What I call a repair cycle. So if hardware breaks down, it needs to be repaired. It needs to be verified. Costs time, costs energy. It's a waste. This is something that most people have seen happening before and experienced, that when you're doing your run, your nice parallel run has been running for 2 days straight, and you're getting there, you're at 80%, and then suddenly one node just completely dies off. Your parallel run, you were not on time to merge it to a different machine, or offload it, or do a snapshot, or do whatever you need to have that momentum prevent from loss. This is something that happens a lot in HPC from experience, but it's something that you don't want to have happen. A transition from here to here is a controlled way, and other way around. This means fatal machine failure, network failure, storage failure, etc., etc. So this is a disastrous thing and it should never happen, although it happens a lot. Basically, there's a funny note of it, is that if you keep this cycle, the control cycle, long, the longer this gets, the shorter this gets, but the less likely this will fail. So in the end, if you keep your machines offline for 99% of the time, the 1% that is available for computation, it will most likely not fail. Right, okay, so if you break this down to what kind of hardware incidents we see, this is from 2014. Unfortunately, I don't have the 2015 data yet, so I have some good estimation I will show you. Is that majority of failures, hardware failures, is memory related. And memory related problems can be detected by something called an MCE or a machine check event. There are components that are connected to the PCI bus. So all these failing components or early failing components trigger something that is being captured and stored in a register in the CPU, and the operating system picks it up and reports it as a machine check event. Doesn't mean that it's failing already, but it can be seen as an early warning, like your orange light on the dashboard of your car when your oil level is too low. The car still runs, but you have to take an action soon. Then there are hardware failures that are not easily detected, but can be detected by automation and scripts. And I mentioned SCAD, which stands for scheduler, which I will elaborate in the next slide, is how we detect these kind of things. This is not technical, this is very high level, but it gives you a bit of an idea. Some other parts are not easily detectable, like a failing power supply, because the machine doesn't have power anymore to pick up the failure and report it. Sometimes you're lucky, you get an early warning. So most of the time you're unlucky and the machine just immediately stops. And that's it. To know that I call this cluster 3. I'm primarily looking at the simulation environment. I'm not supposed to say any names. Cluster 3 is the latest edition that came in 2015. It's not included in these numbers yet. So here we're talking about roughly 4,000 or 5,000 machines. Is that correct? Something in that line. So as many people already mentioned, that we're getting more and more machines, more and more bigger clusters. Next edition is going to be bigger. So moving on. Is that if you compare how much time you have to invest to, well, get just a machine back on track again, so for whatever reason it failed. In 2015 we had 550 incidents on average, so it can be more, it can be less, root cause analysis. Hard drives, very easy to detect. Within 2 seconds you log in, you see your shell is broken, you see weird things in the message. Very easy to detect and to analyze. Sometimes more complex things to analyze are failing infinity cars, things like that. So on average 5 minutes. Then you have to make sure that a case is open so that the vendor can start working with this machine. And after the machine has been repaired by the vendor, it's been given back with a note that it has been repaired. But you have to verify before returning back to production. So roughly it takes 45 minutes per incident to have this machine back on track, and that's in raw average. So in 2014, there was roughly 400 man hours just to get this environment, keep the environment healthy and on track. So that's 52 roughly working days, which is not a small amount of things that are very repetitive. Right, so covering some automation, we do more things, is that because of these repetitive things, we started to automate it. So the current automation detects hardware failures and early hardware failures, so it's mainly reactive at this stage, at least being discussed here. It creates tickets to follow up, it follows up with vendors, it does verification, if the quality verification doesn't work out, etc., etc. So basically, you come in, the first thing you do in the past was to check what went wrong overnight. Now you come in, you get a coffee and see if you have received an email. That's the difference. it does more things than actually is required for the future, and that's what I'm currently working on. It is collecting or making or gathering fingerprint information. Know that a compute node is not a compute node per se. Every node has a bit of their own identity, their own personality. And especially Musli can confirm this, is that compute nodes are not the same. Each compute node acts differently. And because of this, it's very interesting to collect fingerprints, because it will tell you in the future how many, at least tell you at the current time how many times already it failed or why it failed. And in the future you can do some analysis and say, what is the probability it will fail again the next month, the next 2 months, or the next week. So that's something that we are currently working on. It does a quick maintenance cycle, especially in the weekend. What it does, it takes a node of mine and runs a couple of predefined benchmarks and compares with already gathered numbers, compares with other machines, and sees if it's inspected. If everything is fine, it will be returned. This normally takes less than a day, unless something goes wrong, and then the machine will be taking more time to repair. Right. So like I said, we use the scheduler to mainly to detect these issues. And why you say, why is scheduler? GE related products like SGE and UGE allow you to run like others like PPS to run something every interval. UGE, SGE is 1 minute. During this time, it collects information about the load of the machine. Or basically, it runs a script. We extended this script to run a couple of other scripts as well. Very lightweight, so the whole checking cycle should not extend more than a few seconds. It needs to be very lightweight. During that time, we check for specific, easy to find clues and indications that hardware might fail or is already failing at the moment. Like, do I see specific messages regarding the hard drive, local hard drive, these kind of things. So what we do then is we inject, the system injects this into the database. The database running, the automation picks it up and offlines the nodes, and from there on it will be going through the flow of repair. And the maintenance cycle is just a direct injection where you can call through an API that we developed ourselves, and then the machine will be on the same track. So there are many ways to do this. We use a scaler because it's very reliable on machine, so it saves us from running another agent. Right. I'm combining two things now. Is that, like I mentioned, this presentation covers two kinds of automation. One is the failing hardware or problem detection, and the other one is the job failing analysis. I'm not discussing that now. I'm going to discuss it later on in this presentation. But what I try to tell you is that we do a correlation already between what has been detected during a job run or before a job run and what was the outcome of a job that failed. So this is, for example, a single or a bunch of machines that have shown hardware failure that was the root cause of the job to fail. In correlation, what the problem was actually why the machine has failed. So this is to confirm that the health checks that we run every minute are actually pretty precise and good in gathering this information to do work on. This is, I'm not sure if it's visible from behind, this says hardware versus memory. So the job failed because of a hardware related issue. In this case, memory was the culprit of the job to fail. We have different colors for the different clusters, so cluster 1, 2, and 3. And the longer the bar, the more precise this detection was. The time difference between when the job failed and a hardware problem was actually detected. So this is a pretty accurate detection, as in when a job failed in correspondence to the hardware component actually failed. Storage, the job failed because of storage related issues. Am I not? Right. So we saw jobs failing, and in the end it was an event related problem. So it doesn't look like in at first sight a logical explanation, but this is the correlation. As you can see, it's the second most probable cause. So this is something that we should really look into. Storage and memory, if the job failed because of storage-related issues, it can be an NFS server that's not responding, or a high-performance storage that is not responding on time. The third probability is that memory, in this case, has failed as well. Not something likely. Of course, an MPI job failed because an MPI, for instance, InfiniBand, so that this kind of thing makes sense. This is something that's not probable, but yet very interesting, is that when a job failed with a segmentation fault, in this case we have a couple of occurrences where the local disk was the culprit. Right, okay, so people ask me that you did all this work, everything took a lot of energy and effort, but is it really worth it? What is now the business impact? So if you break this down in numbers, so we compare each year, here just for the hardware incidents, and here we do a maintenance cycle comparison between all the years. 2014, this system was introduced at the end of 2014, so we don't have much data, we have some data. So it saved us roughly 130 hours. 2015 estimated, because the data we have is not complete at the time that this presentation was initially created, is roughly 518 hours. And since we have additional compute power, this increased to 570 hours. This is not a small amount of time. If you include the maintenance as well that you can do to prevent, well, to make your environment stronger, to harden your cluster environment, then this is a staggering amount of time that you can save by automation. You can say like, well, if you don't do automation, with including automation, is 1.5 FTE, that means 1.5 employee just doing this full time, day in, day out, verifying numbers, checking things, running your tests, etc., etc. Even without the maintenance, it's still a 70 plus days of engineering time that in this case was completely automated and not required anymore. So, the maintenance cycle, although people say like, you don't need it really, you don't need to do some tests. The maintenance cycle, remember, is to prevent a sudden state change from doing computation into failure. So this eliminates this as much as possible. So this is getting more to a proactive cycle instead of just being reactive. What we do is we take roughly 20 nodes per week during the day and the 75 nodes during the weekend when it's more idle. And over a whole year we have done a full maintenance cycle of each compute node in the whole environment. Right, so you can say we save time. It's good for business. We have made the system so we don't have to spend much time anymore. But is it really effective? Do you really need it? I think you cannot have a good HPC presentation without some formula. So this is my formula slide. What I'm trying to tell is that every component in servers in the HPC cluster is showing this kind of curve. In the beginning, when the computers arrive, there are a lot of failures, and over time it reduces, then it's not stable for a while, and in the end, when MTBFs are approaching and you cross the MTBR, then you see an increase again in failing components. And that's also the end of the economical life cycle of a cluster. Right, so NCEs in the beginning, so mostly memory-related problems. And this is a time frame, it's not really readable, but it's April 2013, and then we go into 14, 15, and now we are in 16. So as you can see, there is not much happening here, so the bathtub curve is pretty flat here. And then you can see an increase of MCEs. and increasing. So this is also the time that they say we have to do something about it because it's getting out of hand. So automation was introduced. You see a sudden drop, which is a good sign. But still, it went up some more. More machines were actually about to fail or showing indications that the stability was affected. It went down a lot. The new cluster arrived, and this was in combination with another cycle of a buffer for machines that were early repaired and still showing issues. So you can see it's going up and down, up and down. I pointed this chart down because it is going down slightly, but yes. So you can see it's a big number of MCEs reported. And again, you can ask the question, is it really relevant or not? Because it's all ECC memory, does it really have effect? Well, yes. So what I do here is I chart the red line, as in how many MCEs are reported over time. And the blue line is the number of jobs that failed. I use a logarithmic scale to normalize, otherwise it will be really spiky. But you can see there's a strong correlation at these time frames where you can actually conclude that MCE has a large influence. And since the introduction of the system around here, you can see the slope is going down. Blue is the percentage of job failure, and green is the job failure, but then in weight. Not every job is the same job. You can have one job that's running like on one node for 10, 20 minutes, and you can have a job that runs on 200 nodes for 5 days. So this is a normalized weight. So in this case, the smaller jobs have more weight in comparison than what it would be without this normalization. You can see the slope is going down, which is a good indication that this automation and repair and being ahead of the trend actually works. But it still means that larger jobs are sensitive or prone to fail over a long period of time. So we don't see a big reduction there, unfortunately. And it can be explained as follows, because we see a big correlation here in the previous slides. However, it seems to be broken here. It doesn't match anymore in the last few months. So the question comes again, okay, if MCEs are no longer the major reason why jobs are failing, then what is? Okay, so the white line here in this chart actually shows you the normalized job failures versus the other components that show here. Blue is MCE. You can see that it's matching quite nicely. MCEs are dropping off and they're at the bottom now, but jobs are still failing. In this case, it was related to external factors like in IPA, NAS, storage InfiniBand. But again, even though we have more indicators why jobs are not successful, this line didn't go down like where it should be around here. So there's still some components missing. This made me realize that we have to do something more than just do this by hand. This is a handmade chart with handmade gathered data that took days to get all the information. Thank you very much. 2 minutes. Right. So basically what you see in the previous chart is that it follows a cycle of success instead of a cycle of misery. We went from MCEs to external peripheral, maybe network switches, InfiniBand, to operating system related problems, to back to application. If you enforce all of these, you go back to hardware failure, then you go into this pile until you reach no error spot. However, the more closer you come to the center, the more challenging it is to solve these problems. So it becomes really hard to solve new problems that you face along the way. And I think we did a full cycle and we around here. It doesn't have to be a spiral, it can be going here, there, but every time you reinforce, the problem moves to a different area, and then you have to solve it on again to get more reliability out of your product. I think we're currently back around here. And you can say, why do you figure out that you're there, that's what you just pointed out? It's basically because of this. This is the number of job counts that have caused issues or did not end successfully. And this is the same job but then in known hours. And as you can see, this is a trend that is increasing again and it's hard to relate it. So most likely MCE, CPU. We also tend to see more sudden death in that we no longer see nice warnings ahead of time that we can step in and say we have to take the machine offline. So we have to stay ahead of the curve, and this time we have to focus again on the hardware. Stabilize the problem, move away. As you can see, we had some storage-related problems in the past that have been minimized to almost zero now. This, by the way, is completely automated. So we have these charts real time, all in, day out, which was quite a challenge because everybody who used to work with GNU plot knows exactly how challenging it can be to make nice charts. This is another automated chart, is that it shows you, and I had to cut out the names of the nodes, but it tells you in the last year how many times a specific node was involved in a specific job issue. I'm almost there, by the way. So, although it doesn't mean that this node is really bad, but it tells you that this node has been involved most of the time when a job didn't work out successfully. This can also mean that this job was more used, so you have to be careful concluding anything out of it. But at least it gives you a hint as where to focus on, what is the weakest link in your chain. Right, so as a result, automation really reduces the overhead and the time you spend to do day in repetitive tasks. It improves reliability. It limits downtime as much as possible. You have to invest some time. I forgot to mention it, but it's roughly 100 hours per year, sometimes a bit more if you introduce a new test. It can really help you to gather information through fingerprinting. It cannot prevent all failures, but at least it gives you a good baseline to say, okay, from here on we have to do some investment and then some manual investigation. But at least it will save you a tremendous amount of time, and especially in growing environments, you cannot live without that anymore. So, briefly touching other automation, like I said, is that we do job failure analysis completely automatic and it's pretty accurate. Still a work in progress, but it's so far. Other thing to do is to do a pre-job verification test. We use it information to produce heat maps in the fabric or in the machine. So we use information twice to not waste CPU cycles. We are working on early environment problem detection, and this one is actually correlated. Is that my goal is to have a model, and I'm training the model to actually do a more accurate prediction when a specific resource will fail. And I'm aiming at compute hardware because switches network it's very hard to put anything there. If power fails, you cannot predict. But compute nodes are, since you have a lot of machines, you can actually, based on their identity and their behavior, you can do predictions as in when this machine will fail. You can use this information to, how do you say it, influence the scheduler to no longer use this node for longer jobs or whatever. You can say this job is still good for 2 weeks, this machine is useful. Other than that, you have to take it offline. So these are things that are still in work in progress. So I want to keep it there. If somebody is interested or has questions, then please fire away. Yes?
Do you have a lot of codes for writing this automation? I mean, do you write a lot of code
Yes.
for this automation? And are you willing just to share it over the source?
Yeah, it's a bigger set of code than I ever intended to become, but it is a quite big set. Things you have to optimize really well because it takes time to collect data and kind of things. So especially the job analysis needs to be very quick because it's running at the end of the job. The other parts can be a bit more, well, you don't have to be really efficient. If you take a north line, it's okay if you take a line 5 minutes longer, but it's a huge set of scripts, binaries. Each environment requires different kind of binaries compiled versus different libraries, so it's not easy to build this set. Once you have this set there, and new clusters come in, you simply recompile binaries suitable for that cluster and you're good to go. So it's an initial investment that over time pays itself back. I hope this answers your question. All right. Thank you very much.